Watch how fluidly this robot coordinates its fingers, wrists, and arms to transfer an object between its hands. To a human, this motion is trivial. To a roboticist, this kind of continuous, real-time physical adjustment has historically been difficult to program. For decades, the engineering bottleneck in robotics has been the cross-embodiment problem. If you trained a neural network to control a 6-axis industrial arm, that math became useless if you tried to port it into a 30-axis humanoid. Their state and action spaces, the specific mathematical boundaries defining what a robot can perceive and how its motors can move, were incompatible. That hardware fragmentation is exactly what the NVIDIA GR00T N1.6 release is designed to bypass. GR00T N1.6 is an open-weight foundation model, meaning its internal mathematical parameters are publicly accessible. Its sole purpose is to act as a universal brain capable of operating across diverse robotic hardware. It achieves this through a vision-language-action, or VLA, architecture. Rather than relying on rigid, pre-programmed code to dictate movement, a VLA is an end-to-end framework. It ingests raw pixel data from cameras and text prompts from human operators, and translates that directly into the continuous motor torques required to move physical joints. By releasing this specific architecture openly, NVIDIA has removed a primary barrier for physical AI research. Hardware startups and academic labs no longer have to spend years building proprietary controllers from scratch. They can download the generalized brain and focus entirely on the physical execution. The path to a universal controller required specific architectural corrections. The original GR00T N1 model predicted absolute joint angles. It calculated exactly where a limb should be in a vacuum. But physical reality involves gravity, friction, and uneven terrain. When the robot's actual position drifted from the absolute prediction, the resulting corrections created a rigid, jittery movement. The intermediate N1.5 release attempted to smooth this out, but it relied on a rigid 4-layer transformer adapter. This adapter served as a mathematical bridge between the model's semantic understanding of the room and its physical motor output. Pushing data through that specific bottleneck introduced processing latency, and in balancing a bipedal robot, a few milliseconds of latency can cause a fall. The primary architectural intervention in N1.6 was to delete that adapter entirely. Instead, NVIDIA engineers unfroze the top 4 layers of the vision language model during the pre-training phase. Rather than translating semantic data into motor data after the fact, the VLM is forced to learn internal representations that are directly aligned with embodied action from the start. At the same time, the model shifted from predicting absolute angles to predicting state-relative action chunks. Instead of aiming for fixed coordinates in space, the robot now calculates its required movement relative to its exact current physical position, allowing it to absorb unpredictable physical disturbances on the fly. To supply accurate visual data for these calculations, N1.6 upgraded to the Cosmos Reason 2B VLM variant. It processes camera feeds without aggressively cropping or padding the images, eliminating the digital distortion that previously impaired a robot's depth perception for small objects. By combining uncompressed depth perception with zero-latency physical translation and state-relative error correction, the VLA transitions from a theoretical proof of concept into a viable, real-time physical controller. To handle both high-level reasoning and millisecond-level balancing, GR00T relies on the dual-system architecture inspired by psychologist Daniel Kahneman's concept of fast and slow thinking. It decouples deliberate cognitive planning from reflexive motor control. System 2 is the slow thinking module. Powered by the Cosmos Reason 2B VLM, it operates at a relatively low frequency of 10 to 30 Hz. Its job is to take an ambiguous human command, like clean up this spill, and decompose it into a logical, stepwise plan of action. This is based on the specific geometry of the room. System 2 builds this understanding using 2 distinct inputs, a SIGLIP2 vision encoder, which translates raw pixels into mathematical arrays for spatial awareness, and a T5 text encoder, which parses the semantic meaning of human instructions. Looking at this architectural diagram, System 1, the fast-thinking muscle, utilizes a diffusion transformer operating at 120 Hz. Token embeddings extracted from the VLM pass downward, feeding directly into the cross-attention layers of the DIT blocks. Inside those blocks, the system uses flow matching. Unlike a text-based language model that guesses the next discrete word, flow matching predicts the velocity of a denoising process. It mathematically smooths out random noise to generate continuous fluid action trajectories. To handle the complexity of this continuous physical denoising, the N1.6 upgrade doubled the capacity of the DIT head, expanding it from 16 layers to 32 layers. To make sure these 32 layers can actually speak to any hardware chassis, GR00T uses embodiment-specific MLPs. These multi-layer perceptrons act as specialized translators, projecting the varying telemetry of different robots into a single unified latent embedding dimension that the central model can read. By decoupling the slow cognitive planning from the high-frequency motor translation, GR00T resolves the latency trade-off. The robot can think deeply about a complex room without its legs freezing in the process. Even with a flawless architecture, training a generalist robot requires data. Historically, roboticists relied on human teleoperation, physically puppeteering a robot to teach it a task. But teleoperation is slow and expensive, making it difficult to scale to the level required for broad, general-purpose intelligence. This diagram illustrates NVIDIA's data pyramid methodology. At the base is scale, ingesting massive volumes of internet-scale video. The middle tier focuses on variation, absorbing millions of synthetic trajectories. The peak is specificity, using sparse, real-world teleoperation data. To understand the sheer volume of this pipeline, look at the open NVIDIA Physical AI dataset. It contains over 314,000 cross-embodiment simulated trajectories and millions of real-world telemetry tokens, specifically covering complex tasks like bimanual manipulation. Structuring the training corpora in this exact ratio is deliberate. It forces the neural network to learn the general physics of the real world from the bottom layers, long before it attempts to memorize the specific hardware limitations at the peak. That massive middle tier of the pyramid is powered by the Cosmos World Foundation models, serving as the generative engine for the entire simulation pipeline. Using a workflow called the GR00T Mimic blueprint, developers can record a single human demonstration of a task, and the simulation engine extrapolates it into thousands of geometric variations, changing the lighting, object placement, and friction models instantly. The GR00T Dreams blueprint takes this further. From a single static image and a text prompt, the DreamGen pipeline generates entirely novel neural trajectories. These are mathematically viable video predictions of future physical states, showing the robot successfully completing a task it has never actually seen before. Inside these generated environments, simulated robot agents practice complex tasks, like constantly adjusting a grip on a shifting object in a purely virtual space. Because this happens inside the Isaac Lab framework running the Newton physics engine, these synthetic trajectories strictly obey real-world gravity, mass, and rigid body collision dynamics. This enables accurate sim-to-real transfer. The low-level motor intelligence trained in the simulation translates zero-shot to the physical hardware. Zero-shot transfer means the robot can execute the maneuver in the real world on its very first try, relying on virtually built muscle memory. By synthesizing world data with physical accuracy, the VLA bypasses the physical limits of human data collection. It masters the geometry and physics of a verb in code before ever moving a physical servo. The actual value of this architecture is proven entirely by its performance against established robotics benchmarks. On the Libero benchmark, the LiRobot implementation of GR00T N1.6 achieved an 87% average success rate, exceeding the original N1.5's 76%. This persists across hardware. N1.6 consistently executes tasks in SimplerEnv and Robocaza, whether driving a Franka Panda, WidowX, or Google Robot Chassis. The efficiency of the data pipeline is equally rigorous. In real-world tests, researchers achieved high physical success rates deploying the model onto the Unitree G1 Humanoid after post-training it on only 1,000 human demonstrations. Most critically, the zero-shot generalization metric, the ability to succeed at novel, untrained tasks, jumped from 13.1% in the original N1 release to 38.3% with N1.6. These metrics confirm the core thesis. Training massive neural networks on physics-constrained synthetic trajectories successfully bridges the sim-to-real gap for highly dexterous, multi-contact robotics. Hardware manufacturers are already moving to integrate this architecture. Companies spanning from Boston Dynamics and Agility Robotics to 1X, Fourier, and Unitree are actively deploying this foundation model ecosystem to drive their physical chassis. For independent researchers, NVIDIA strategically integrated GR00T N1.6 directly into Hugging Face's open-source Lee robot library. This provides the community with unified dataset APIs and standardized evaluation tools right out of the box. On the deployment side, the entire VLA software stack is optimized to run locally on the energy-constrained NVIDIA Jetson Thor robotics module, keeping the intelligence on the physical machine instead of lagging in the cloud. We are watching the consolidation of a highly fragmented robotics industry into a single, unified, and open software standard for the future. GR00T 1.6 is the most capable open-weight humanoid model available. By providing the weights, training data, and simulation blueprints freely, the transition toward general-purpose agents has moved out of proprietary labs and onto a public repository accessible to any researcher. In our next episode, we will go hands-on with the actual code, detailing the specific workflows required to fine-tune these models inside Isaac Lab.